This is Geometry Chapter 15, Lesson 4, Volume of a Prism. So we talked a little earlier about the difference between volume and mass. Mass deals more with weight. Volume deals with the actual space that a three-dimensional object takes up, right? The space that it displaces, okay? So look at the top of page 640 of those pictures. You know what kind of candy bars they are. Top left is a Three Musketeers. Top right is a Snickers. Bottom left,
Butterfinger.
my fave. Bottom, I love Butterfingers.
Amazing. Butterfingers are amazing. They're delicious with ice cream.
If I go to Sonic, I'm getting a Butterfinger, blah, whatever it is. Okay. Our Heath bar. Oh, I love Heath bars. Okay, they don't have one. The bottom,
Milky Way.
right, Milky Way. That's your favorite? Okay, you can't just find a Milky Way just anywhere. Or a Three Musketeers. You have to go to Dollar Tree. You know, I know this because I bought these before. And I just know I'm going to Dollar Tree. Okay. Which one would you think has the greatest volume?
Snickers.
Probably a Three Musketeers. It looks taller and as wide as all the other ones. It takes up more space. You agree? Okay. Now, which one do you think has greater mass?
Snickers.
Snickers. Those peanuts are probably heavy, right? And the caramel. And yeah, I think it's probably a little weightier. It could even, no, the Butterfinger probably doesn't. So, just because a prism, these are prisms, you never knew candy bars were actually prisms, did you? Just because it takes up more volume, which is space in which it occupies, it doesn't mean that it's heavier or it weighs more. That is more like mass, all right? So in the previous lesson, we looked at lateral area and total surface area. Remember the lateral faces? The lateral, for a prism, the bases have to be congruent, right? And the lateral faces are parallelograms, right? If it is a right prism, that means this lateral face is perpendicular to the base, and the altitude of the prism would be this right here, right? The length of one of your quadrilaterals. But it is it's the length, the altitude of every prism is the height that is perpendicular to both sides. So if I draw a line, this line has to be perpendicular to both of the bases. So if your bases look like, if it's looks something like this, right? Imagine that being a three-dimensional object, right? Then your altitude, that would be your altitude. It's the distance between the bases perpendicular to both of the bases. Does that make sense? Has to be perpendicular to both of them. I already told you the volume of any object is the amount of the space it occupies. It has nothing to do with how heavy it is, right? Volume could be greater than mass, or mass can be greater than volume, right? Volume simply has to do with how much space a three-dimensional object takes up. All right, now, this is an important concept, a cross section. All right, so here is a piece of my gum, right? I cut it, and this would be the cross section. this shape would be the cross section. What is the shape of the cross section? What do you think it is? What? Oval? Did somebody say oval? I think it's an oval. It's could be an ellipse. Would be the right term. Look, I'm trying to hold it up and it's going out of camera range. The cross section is if I cut it, what this shape is.
Isn't how you cut it though?
Probably going to be the same even if I cut it at a diagonal. It's still going to be in that sort of a elliptical shape. Okay, here now. Imagine this if it were, I should have made it a square, okay? And I cut it. And what would you say the cross section of this is?
Rectangle.
Rectangle, exactly. I tried to make it as rectangular as possible. So what is a cross section? It's any solid that is intersected by a plane, and the plane that I intersected this with was a knife, right? That knife was the plane. And with all the candy bars, they were intersected with the plane of a knife. And we can see with their cross sections, those pictures are actually the cross sections of those candy bars.
They're all rectangles.
They all appear to be rectangles. We'd have to kind of
Even it out.
take the top off a little bit because they all have ever so slightly parabolic, yeah, we call it parabolic tops. All right. So, Cavalieri's principle. Cavalieri's principle says that if I have two solids that lie between parallel planes. Do you see those parallel planes in those two solids? That picture at the bottom where you see B, and H. One is the prism on the left is a what?
Rectangular.
It's a rectangular prism. The prism on the right is a triangular oblique prism. Got it? The bases on the left are rectangles. The lateral faces are probably rectangles as well. The bases on the right are triangles with the lateral faces being rectangles, but it is oblique. So there's a plane on the bottom and there's a plane that runs through the middle. You see the brown section, the brown colored area? That's what the cross section looks like. So the cross section for the one on the left is a rectangle, and the cross section on the right is a triangle. Does everybody see that? The cross section is a triangle. Here's what Cavalieri's principle says. If I have two solids, two prisms, such that they are intersected by two planes that are parallel. You see those two planes that are parallel? Like the white clear sheets? You see that in the picture? If they are intersected by two planes such that the planes are parallel so that their altitudes are the same between the planes. Does that make sense? The altitudes of both of those solids would be the same. If the area of their bases are equal, so if the area of that rectangular base is equivalent to the area of that triangular base, then the volume between those sections is equal. Okay, that was a big mouthful. What does Cavalieri's principle say? If I intersect two solids, and that with two planes, and the two planes are parallel, it makes the altitudes equal. Their volumes will be equal if the area of their bases are equal. So if the area of this rectangle is equal to the area of the triangle, then the area, the volume of those solids between those two planes are going to be equal. Make sense? Yes.
But they also have the same height.
Well, they will, because what did I do? I intersected them with two planes that are parallel. So they have to have the same height because my planes are parallel. So that section, that volume is going to be equal. The volume of those prisms between the planes is going to be equal. Does that make sense? Yes. All right. Turn the page to page 642. Why is that true? Because what is the volume of a prism? The volume of a prism is the area of the base, whatever shape it is. If it's a circle, what's the area of the base? Pi r squared. If it is a hexagon, what's the area of the base? Mr. squared. If it is a rectangle, the area of the base is going to be length times width. If it is a triangle, the area of the base is going to be 1/2 base times height. The volume of any prism is always going to be the area of the base times its altitude, or times its height. And remember that height is the altitude. It's a perpendicular, it's this perpendicular line between the two congruent faces, the bases. Got it? And so the corollary to postulate 14 says the volume of a rectangular prism is still the area of the base times the height, but the area of the base is length times width. So it's length times width times height. If it's a cube, then the length and the width and the height are all the same value, right? Yes? So it's the measure of any edge cubed because it's the same value. Does that make sense?